Hello, this will be the last video in Chapter 6. This is a special one in which we're going to use one of the reactions we learned, specifically the hydrogenation reaction, to measure the stability of alkenes. Now, what does that even mean? Well, as you may know, some alkenes are more stable than others. For example, 2-butene is more stable than 1-butene, and cis is more stable than trans, and those sorts of things. Stable basically just means has less energy. And so what we're really going to be doing is measuring the energy of different alkenes by using the reaction called hydrogenation. And you may remember that's the one where we just add 2 hydrogens to the double bond of the alkene and turn it into an alkane. We can measure the delta H for that reaction, and that's what we mean by heat of hydrogenation. So please, at this point, if you haven't already done so, stop and read section 6.6b. It's on pages 236 to 238. It will explain what we're talking about in this video. Hopefully you can use the video and the reading to complement each other and understand the topic. Here is the fact. When 2 different isomers react to give the same product, the difference between their 2 heats of reaction must be due to their initial energies. I'll explain what that means here in just a minute, but let's make sure we're clear on what we're talking about. 2 different isomers. First of all, they have to be different and they have to be isomers. So for example, 1-butene and 2-butene. These are isomers of each other because they both have the same formula, C4H8, C4H8. Furthermore, trans is also an isomer, so these 3 are all isomers of each other. And when they react with hydrogen and the catalyst, that's the hydrogenation reaction, all 3 of these would give the same product. So that's just N-butane. So that's what we mean by different isomers reacting to give the same product. Then, notice we can measure the delta H of this reaction. It turns out it's negative 30.3 kilocalories per mole. It involves a kind of a calorimeter called a bomb calorimeter because you're literally doing this reaction in a closed container. But it's not that different than the coffee cup calorimeters that you used in general chemistry to measure delta H's. Well, it turns out that the delta H for this reaction, 1-butene, is negative 30.3 kilocalories per mole. Now, let's just talk about what the negative means here for just a minute. It means it's a exothermic reaction. Heat comes out. So that must mean that there's more energy in 1-butene and hydrogen together than there is in butane by itself. Okay, so somehow when these 2 things react with each other, they give off energy. So what we might say is that this is higher energy than this, but it's really this and hydrogen together that's higher energy. And hydrogen does contribute quite a bit to it. Nevertheless, this reaction has a negative 30.3 kilocalories per mole delta H. When you do the same reaction on cis-2-butene, you only get out 28.6 kilocalories, so less energy is evolved, given out of that reaction. And trans-2-butene, when you do the same reaction, only gives out 27.6 kilocalories per mole. So they're all highly exothermic, but this gives out the most energy, then this, and then this, of those 3 isomers. So what does that mean? Well, since they're all going to the same product, 1-butene, all 3 of these reactions are downhill to the same place. So since they're different from each other, it must mean that they have different amounts of energies to begin with. In each case, we're adding 1 hydrogen, so that's not the difference. The difference must be the alkene itself. So this alkene must be higher in energy than this one, which is higher in energy than this one. And so notice that 1-butene, when it reacts, has 1.7 kilocalories more energy because this gives off 30.3, this gives off 28.6. The difference is 1.7, and so that must mean that something about 1-butene makes it have more energy to begin with than cis-2-butene has, and the difference is 1.7 kilocalories. Now, it's not a lot of energy difference, but it's significant. Okay? And furthermore, since this was 28.6 and this was 27.6, somehow cis-2-butene must have more energy in it than trans-2-butene has, simply because when you burn it, to get the same product, you get out more energy from cis-2-butene than you do from trans-2-butene. By the way, if you were going to use these as fuels, which one would give you the best amount of energy, or the amount of heat, from burning them? Well, this one would because it has the most amount of energy to begin with. Okay. Anyway, what we now have been shown is that 1-butene is less stable, meaning it has more energy, than either of the 2 butenes, and that's going to be what we call the Zaitsev rule. Basically, that says that the more interior a double bond is, the more stable it is. And furthermore, Cis is less stable than trans, and that's what's going to be called the trans rule, that somehow a cis double bond is less stable, meaning it has more energy than a trans double bond, everything else being equal. So here's a question. Could we use the same method to compare the energies and stabilities of these three alkenes that we just talked about with that of 1,3-butadiene? So here's butadiene. If we hydrogenate it, it would take two hydrogen molecules to do it, because we'd have to put hydrogen across that double bond and hydrogen across that double bond. But we would still get the same product, which is N-butane. Could we use that to do this, to compare the stability of that molecule to these? And the answer is no. Why not? Because, as I said, it takes two hydrogens, and that adds considerably to the amount of energy to start with, because hydrogen has a lot of energy in it, which, by the way, is why hydrogen is such a good fuel, because it has so much energy in it. So it gives a much bigger amount of energy, not because the alkene is different, but because you're using two hydrogens instead of one. So you can't do that. Well, remember the original rule I said is you can compare them if they're isomers, but notice that this is not an isomer of these three, because its formula is only C4H6, whereas these are all C4H8, so it's not an isomer, so you can't use this method to compare stabilities. Could we use it to compare the stability of 2-methylpropene, which is also C4H8, so it's an isomer of these other three? Could we use the same method to compare its stability to the other three? And the answer is no. Why not? Because it gives a different product. Since it's not the same product, at the bottom of the graph, it's going to be different, and so you're comparing apples to oranges. You're comparing two different starting materials and two different products, so you can't really compare it in terms of which starting material is more stable. Are there other heat-sip reactions that we could use? And the answer is yes. So very often heat of combustion is used. So all four of these isomers do in fact give the same products. In the case of C4H8, they react with 6 oxygens to give 4 carbon dioxides and 4 waters, so you can compare their heats of combustion to see which one is more and less stable, and what you would find is that 1-butene is the least stable, and then cis-2-butene, and then trans-2-butene, and notice that 2-methylpropene gives off even less energy, 603.3 as compared to 604.7, 605.7, 607.3. So combustion is even a little bit more useful, because even compounds that wouldn't give the same alkane, in fact, give the same combustion product, CO2 and water. But they still have to be isomers to start with, because you still